All right.
And
Now we have George. How is it pronounced? I always mess up people's names,
Georg
and I'm always
Hase,
embarrassed.
Hase, Georg, or
Georg.
George, if you like.
Hi, Georg.
Yeah. Hi.
Welcome.
Hi. From adjusting to changing times, maybe to adjusting to changing data. It's something more
this is
simple,
even
maybe.
better transition than the ones we've been
Nice.
making. So yeah, let's
No,
talk
he's
about
been
FSharp
using the word adapt to just once too often to be a coincidence, I guess. But but yeah.
All right, over
Yeah.
to Georg. And
Hi. Thanks for having me. My talk today is going to be about FSharp.Data.Adaptive. It's a library for incremental computation in the FS project incubation space on GitHub. And I think most people are not familiar with the term incremental computation, so let me just quickly outline what we're talking about. Basically, it's all about programs that react to input changes. So consider your classical program like here on the bottom on an Excel sheet or something. You define some input cells and you define this cell here to be the sum of the other two. And every time you change one of the inputs, you obviously want the sum to be correct, so it needs to be updated in order to reflect the input changes. Another example here are classical makefiles. They are not really a running program. They're instead caching things to disk and reusing what is not touched by any change. So basically, the goal is to compute only what is necessary whenever something changes. To do this, we obviously need to sort of track dependencies in input code and re-execute affected parts whenever some input changes accordingly. So there are many attempts, have been many attempts to do something like this. There have been compilers automatically generating incremental code from standard functional code in ML, I think, and OCaml is one. But what we wanted to do is actually, we wanted to do this as a library in F#. And so it's more or less obvious that in order to do that, you need to put your values into some sort of cell. So it's basically a container type that manages all the dependency information, and you put a value in and you can get it out again. And you need combinators for abstracting over those cells and mapping those cells, etc., etc. And of course, you need some sort of change propagation mechanism. This here on the bottom is a very, very reduced variant of how this looks. So it's basically an AVAL, which stands for adaptive value. Excuse me if I confuse incremental and adaptive all the time. It's to me, they mean the same thing. So essentially what you have is a dirty thing, which basically tells you whenever the value may have gotten dirty, and you have, no pun intended, and a get value function for getting the latest value out of the cell. So these cells then form some sort of dependency tree, and whenever you change an input, you can just, by re-executing the necessary code, get the correct output again. So here's a little more complete overview of what we do. It's basically the adaptive value I just showed you and something special or some decision we took. We have a special type for changeable inputs. So this means we have a distinction between changing values that a user can change versus values that change in respect or in reaction to some input change. So an adaptive value is something that might change without you knowing it, except for when you observe whenever it's dirty. And a changeable value is sort of a user input, something you can modify in your program. And here are the most basic combinators. Of course, there exist tons of more combinators and more complicated things, but these are just the basic building blocks you need for using adaptive, more or less. So you have constants. You can obviously map over a value. You take a value of A's, you have a mapping function, and you get a value of B. And the only real interesting one here is the monad bind, which basically allows you to formulate dynamic dependency trees, meaning that the dependency tree structure for your value, for this value you get here, depends on a value that again is sort of a product of the dependency tree. So all of this might seem a little abstract, so I'm going to give you a demo. All the code is, or all the demo code is on GitHub. It's all public and it should be pushed as far as I remember. And I'm just going to show you three very basic examples, and no, two very basic examples and one more a little involved example of how you can use this library and what it can solve for you. So to start out, I have a very simple problem. I have two inputs here. I hope the text size is okay. Can make it a little bigger. Basically, you have two input cells. They both are integers at the moment, and they just have a value 10. And what you want to do is you want to just the same thing you do in an Excel sheet. You want to take both cells and sort of sum them together. And you want the output to be an adaptive value again. So how does this work? You go here, you say, okay, there's a map2 combinator, which wasn't on my slides, but there's also 3 and 4 and so on. And then you get the dependent thing. Okay, you can basically force the thing, which is actually a shorthand for what I had on the slide. It's called get value, and it needs an additional little thing. Don't worry about what this is at the moment. And then you can get the value out, and obviously it will print 20. So the next important thing, or this is just a plain thing calculating something lazy, the important thing here is you can change those inputs. So you can actually mutate input 1, and in response to that, sort of reevaluate the value of the dependent cell, which should be 2 plus 10 now, and you see that it actually evaluates to 12. And also your print here, the little print we snuck in, always tells us when the mapping function is evaluated. So one important thing to note is that initially, of course, the mapping function needs to be evaluated with 10 and 10. When you change the thing, the change itself, which is the important part here, doesn't evaluate it. So we don't see any print. The print happens here inside when we're evaluating the cell. So the entire system is lazy. This has various benefits, and I'm going to come back to that. And yeah, I'm coming back to it right now. Yeah, and when we force the thing, it all gets updated again, and we get a consistent value for 12 in the output. So we can also change two inputs at once, of course. So we may change the one to 40 and the second to 2. And this here, the transact block takes care of updating the entire dependency tree, or telling the entire dependency tree that it needs to be reevaluated whenever someone wants to know the value. What we could also do here is we could use two transactions, which in our system actually doesn't make much of a difference. Sorry, I need to switch my keyboard layout. And run that again. And as you'll see, it will just do the same thing, and there's no double evaluation in that. This, for example, would be the case if you use something like reactive or other eager evaluation systems. You wouldn't have a chance to sort of batch those two changes without any lazy system. Okay, so I guess that's the most primitive example you can come up with. A little more intricate example is here. I mean, I thought about it long, what a good example would be, and I came up with a pretty boring one as far as I'm concerned. But it shows what is necessary to understand the thing. So basically, you have a database of changeable amounts of fruit. You have apples, you have oranges and grapes, and you have, initially you have 10 apples and 3 oranges and so on. Now consider someone having a fruit of interest. Basically, I'm interested in apples. I'm saying here, okay, I'm interested in apples. And what I want to compute now is the amount of the fruit of interest, so to speak. So I know it's a silly example, but whenever the fruit of interest, I go here, I say, okay, take the fruit of interest, I get its name, look it up in the table, and I will get a count. This count is again, an adaptive value. For reasons to show you how the evaluation works, I do a sort of identity mapping here, just to get in a print that shows how the system evaluates things. Essentially, I could just return the count here, but yeah, for illustration purposes, this is here. And if I don't find the fruit, the amount is sort of implicitly 0. Yeah, that's the very, very simple database. Again, I can force the thing, so I get the amount of interest. The fruit of interest is sort of a input cell. It's a changeable value. I can simply get its value via the property. I can, yeah, let's see what this does. Initially, this prints, okay, I'm from above here in our bind function, we say, okay, we need to look up the apples. Then in here, we say, okay, we calculate the amount of apples, the calculation actually being quite trivial. We just return the value. And finally, our print here tells us, okay, we have 10 apples, as expected. And the interesting part is now, okay, I can change the amount of oranges here, and nothing depends on it. So if I set the amount of oranges to 4 and force the thing again, nothing is computed, nothing happens. I can just reuse my previous cache value here. When I now switch to the oranges, of course, everything needs to be recomputed, which the system correctly identifies here. So I need to look up the oranges, I need to calculate the amount, and finally I can respond with, okay, I have 4 oranges after the change you just did. So that's quite simple, and but it's actually quite powerful. It's basically a system for memoizing things without the need to manually sort of memoize everything in your functions. And one little thing I'd like to show you is basically how we did lists. So the naive or obvious way to approach lists would be to put them into an adaptive value or a changeable value and just use a plain list from FSharp. The problem with that is once you start mapping on these things, you quickly realize that your entire list is treated as a value. So this means when I do this here on the list, I want to multiply every element by 2, and I print a map for everything that happens. So initially, everything seems good. I get a new list. It's 2, 4, and 6, and the mapping function is run on 1, 2, and 3. That's sort of what I expected. But as soon as I change the list, something happens, and I start realizing that this is not the thing I really intended. So of course, the whole list is treated as a value. The whole list mapping here is re-executed, and it obviously maps the values 1, 2, and 3 again, even though I already knew what their output value was. So the library also provides something to improve on that. So in order to sort of abstract over that, it's a special type. It's called CList or changeable list, and A-list for adaptive lists, just like with values. And with A-list, you can essentially do exactly that and get the expected semantics. So you create a list of 1, 2s, and 3s. You map over it. Again, I print whenever I map something. And you get an output list. You can force it. The return type here is not an F# list. It's something more complicated, but it's basically a sequence. So we can see the same thing. So with our A-list, the initial evaluation basically does the same as the one before. It maps over the entire list and returns a new list with the multiplied values. But when I sort of prepend or add a 0 value in front of the list and force it again, all it does, it executes the mapping function for the new 0 element and returns me a list with the correct output. So the implications of this are if your mapping functions are expensive here, or if you need to open resources or read a file or whatever, only the one file you touched will ever be read, and all the others will be just cached values that are managed by the system itself. So something a little more interesting, for example, you can take the mapped list we had, the one with the even numbers, and also sum them basically, again with a little print to show what happens. And when you sum the list, you get an adaptive value of integer. You can print the sum. So initially, of course, you get all the elements. You get 0 to 6. And the sum of the whole thing is 12. And you can also add an element. Add is append an element at the end, basically. I can add 10 at the end, and I can look at what happens when I force it. First of all, the mapping function needs to be evaluated from above. We had a 10 and we need to multiply it by 2. The next thing that happens is, okay, we need to plug it into our sum. So our sum needs to add the value 20. And in the end, the output is just 32 as expected, as if you would have computed that on the entire list from scratch. Yeah, for sum, there is a special thing. You can actually remove values since subtraction exists for, there is an addition and a subtraction. I can actually remove one value without recomputing the sum. We cannot do that for arbitrary folds, but there is an abstraction in here or in the adaptive library for creating things like this sum that basically support adding and removing things from and to lists. So I hope that gave you some ideas in your head of how this could be used. Here are basically what ideas and things we used it for. It really comes from our real-time rendering engine, the Aardvark rendering engine, and we've developed it, or the whole adaptive incremental system, for about 13 years now. And it was initially part of our rendering engine and then became a standalone thing for others to use it as well. Basically, what we use it for in our real-time graphics system is for expressing dynamicity everywhere. So we express dynamism in scene descriptions, in transformations, in lighting conditions, in all sorts of things where the rendering system sort of needs to react to small input changes in a huge scene, which is sort of similar to what user interfaces normally do. You have a large user interface with lots of components and stuff. And basically, when one of your texts or something, or one value changes in your model, most of the time only one or two components are actually needed to adapt to that value. And most of the rest of the entire user interface remains untouched. So it's basically a performance improvement for user interfaces as well. It has recently been used for IDE tooling and FS autocomplete for adaptively sort of recompiling FSharp files in the autocomplete extension stuff. It could also be used for database views. There have been attempts, although I have to admit some combinators are missing on our side for that. But conceptually, it sort of does the things database views do. And it can basically be used for anything that needs to adapt to inputs or to changing inputs. So every program where a user sort of changes values can most likely benefit from a system like that. So just a very quick overview on how this works. Basically, you have a little code here that produces this value here on the right, which is called D in the code, an intermediate cell, which is called C, and two inputs A and B. When I change A to 3, the transact here, the function you call, basically starts visiting this tree. It goes to A, marks it as in red or out of date is the name in the code. Marks it as out of date, gets all its outputs. These are the white arrows here, and basically walks to all the outputs and makes them out of date too. There's way more sophisticated stuff in there for threading and queue. You need to priority queues and stuff for that. But the basic concept is you go here, you say, okay, this is also out of date. You delete the cache value in order to avoid memory leaks here. You do the same here, and basically then transact exits. When you force the output cell asks the intermediate, give me a value, which it can't, so it asks its intermediate value, give me your value. And as the evaluation sort of unwinds the stack or walks back up to the calling node, it evaluates the values it needs, and on the output returns what it needs to return. A few words on our implementation. Our implementation, or the library itself, it has APIs for values, for sets, for lists, and for maps. It's pretty, I showed you the values and the lists, but similar things exist for sets and maps. It's quite well documented, and it's really well tested, since it's been the greatest pain for any developer. If you have a problem in your adaptive library, the most common problem you have is something doesn't get executed and should be executed. So you're sitting there and don't have anything to debug. We tested all of the combinators against reference implementations, which reevaluate everything on every demand. So whenever you force the combinator, it basically reevaluates anything on the inputs, and we test the adaptive implementations against those stupid, or they are so stupid they must be correct implementations. It's basically thread safe, so which means you can use unrelated parts of the dependency graph in parallel. You can have one thread doing this and one thread doing the other thing, and the dependency graphs don't get in the way of each other. You can also use threading on one dependency graph, but there is a consistency problem when you extensively use threads. It's too intricate to explain in detail, but essentially it's pretty rare, and the entire system is eventually consistent, which means take this graph here on the right, you change a, and the sum here in the end should invariantly always be 0. So basically you take a by -2 and a by 2, and you sum the two, so the sum should obviously be always 0. And if you bombard this thing with threads pushing changes and threads pulling changes or values out of it, you may eventually see an inconsistent value, but only for a very short period of time. And this was, for our applications, this was just acceptable. Basically, user interfaces showing a wrong value for 1 millisecond and scenarios like that. Yeah, but I just wanted to mention it, and I'm greatly encouraging people to look at it and find something how we can fix that. Yeah, the whole library conceptually has no memory leaks. I cannot guarantee that there is not one single cache that doesn't leak. So if you find anything with it, please contact us and we're happy to fix it if we can. It also works with Fable compiler, so you can use it in your Fable or F# to JavaScript projects. There is recently an experimental asynchronous interop, basically with tasks. You can have an adaptive value of tasks basically as its own thing, where you can support cancellation with somebody wants a value and then decides he does no longer need the value, reevaluates it while inputs change, things in that sort of direction. If you're interested, just get in touch. What I have now, if there's enough time left, is a little application demo, basically something showing a less toy program, showing something really interesting with it. This example is written in with the Aardvark DOM library. It's a rather new thing. It's basically similar to what Elmish React does or React in general does, just in an F# context. And this here is executed currently with the WebAssembly Blazor backend in the browser. But just a very quick thing, this is basically the counter example every one of you will most likely know from the Fable and Elm presentations. So you start with a state. In our world, the state is a changeable value, so we put it into a cval. Here we have a little HTML UI, we have a header. The header should contain the content here, so we take the state, we say, okay, map over the state, make a pretty string out of it, and put it in the header. Also, when the value is negative, we want to add some styling to it. We want to make it red, and if it's not negative, we don't want any styling. The reaction here, actually, we have two buttons. We have plus and minus. Plus and minus on click basically increment or decrement the value, and that's just how we use adaptive for user interfaces, basically. Another thing is we're from real-time rendering, so of course we can render something. We have here a render control, which basically looks like an HTML element. It also is an HTML element. It's just a canvas. We do some styling, and basically we have the same sort of API here. So we want to render a box. The only way to create a SG is for scene graph. The only way to create a scene graph, or the only node type, is actually SG. So it's a little different to HTML, but the rest of the syntax is very similar. and it has different attributes. So basically, we want to take our state, and we want to translate something. The something coming here on the bottom, it's a box actually. Take the state, and whenever the state changes, this is a 3-dimensional vector, nothing more. We want to translate in the z direction. We want to translate it up. And there's some other thing. We want to rotate the box around the z-axis with time. And yeah, finally, we render a box here, a blue box, and apply several attributes to it, which all is sort of similar. And if you click on the box, we want to reset the state to 0. So let me just show you what the program does. Here's our little program. There's our blue box. It rotates around. We can, with our buttons, increment and decrement the counter. Oh, I didn't show you the red boxes. The red boxes are a list of things, or an adaptive list. So we can make the count negative. We see the style change, and it's a very, at least for me, it's a very neat and tidy notation for dealing with change in this API. You can react to discrete changes. You also have sort of a abstraction for time here. The rendering system actually provides the clock here for the time. So whenever a frame is rendered, you can rotate. You can also use dynamic dependencies here. So if you decide, okay, there's an active trigger or something, you can turn off the rotation, and all these sorts of things more or less fall into place like in a functional Elm-like program, with the big difference that this view function itself here is exactly evaluated once. So if I were to, I don't know, load a huge file in here, this would happen exactly once. Or if I have complicated stuff building my AI, this only happens once. And all that happens frequently, so to speak, is these little functions here, and the reactions to them, of course, in the backend. So yeah, here's the set example. Where is it? Do I find it? Here's the set example. So basically I say, okay, create 1 to state boxes or to count, and then I create red boxes that are just translated to the according position. These are the little ones you see here, and when I click on them, I decrement the count by 1. So yeah, this is more or less what we use Adaptive for. If you have any ideas or questions about it, do not hesitate to get in touch. We're almost always on Discord, and of course you can reach me via mail or directly via an issue on GitHub. Thanks, and I'll be happy if there are any questions or if there is time.
I think
we have a few questions there.
Okay.
Yeah, and we haven't overrun yet, so
yeah. Let's do it now.
Something
Yes.
about
Okay.
this. Let's have a question. Can you pull it up?
I'm laughing because I prepared that slide in the morning today, answering that question. It's more or less. Let me just see. Where's my backup slides?
This is very good preparation there.
No, a friend of mine actually said, be prepared for this question.
I see. Nice.
Was it Vladimir, who's your friend?
No, not really. Sorry that this takes so long. I made a PDF out of the presentation, and now I can't find the original one. Here it is. The PDF doesn't include my backup slides.
Nice.
Yeah, essentially, here's a little explanation for that. So Rx and observable basically focus on events and not values. That's a sort of a semantic difference. The problem with reactive really is that you cannot really express a changeable value. You can express a stream of events, and whenever you want to sort of observe the latest value of that stream or consider the mouse position, you want to make the mouse position a changeable value, and the user moves the mouse, everything is nice, you get your mouse positions out of your IObservable. But as soon as the user does no longer move the mouse, you have two options. Either the system can always store the latest mouse position on every mouse move for all future, or you can't just use Rx. So it needs to be a living thing in order to produce the latest value. Whereas adaptive sort of lazily creates that latest value if necessary directly from the input. So I don't know if you have very expensive computations on your mouse position. In Rx, you basically need to execute them all the time, every time your mouse moves, in order to have a latest value should anyone demand it. So this quickly becomes unmanageable if you have large dependency trees. It's also, Rx is obviously eagerly evaluated. You can get around that by sort of creating observables with lazies in them or something more complicated. Yeah, adaptive provides collection data types, which Rx doesn't, as far as I know, or incremental changes to collection data types. And another thing is adaptive allows for batch changes. So you can flush 10 changes into the system at once, and all the redundant reactions won't happen. So I hope that mostly answers it. What the difference to?
Very cool.
Yeah.
All right, I think we are finally starting to overrun a little bit.
Yes.
So thank you, Georg, for a great talk about
Thanks
a
a lot.
great project.
Yeah.
There's a few more questions on YouTube, like where to get the link and circular dependency. So maybe check out the YouTube and
Quick disclaimer: no circular dependencies.
Okay.